Feature engineering. Feature engineering is the means to an end goal of classification, regression, whatever. It's often what matters the most, and metrics are the key to feature engineering. So we're going to introduce feature engineering with 3 additional metrics in this video. I like this quote: "Coming up with features is difficult, time-consuming, and requires expert knowledge. Applied machine learning is basically feature engineering." So not all features in the data set are of equal importance. Some features may not be necessary, or they may be misleading. We may need to use weighted methods, weighted nearest neighbors, weights both in comparisons and in predictions. So which features are we going to use, and how are we going to use them? How are features interrelated? What is giving us the prediction of the topology of the data set? So feature engineering is essential. It's the use of domain knowledge. So you have to know something about the scientific or business or technical or engineering field so you can create and modify features so that algorithms work. Algorithms are not scientists. Big data sets tell many stories, but applications, usually we only want one of those stories. So feature engineering is using your scientific, business, technical knowledge so that in that context you can focus the data on a particular application. And most data scientists spend most of their time and most of their applications doing feature engineering. Feature engineering uses metrics. Anytime you modify a set of data, you should measure how and how much it was modified. See, results can be due to modifications rather than the data. For example, if you impute missing values with a global mean and then you do some kind of a regression algorithm, it will be biased toward that global mean. So we often evaluate feature engineering efforts using supervised learning, as assessed by metrics. There are also metrics for unsupervised learning, and we'll look at least one of those. So this is going to be sort of an overview video. We can't get into every possible scientific domain where these applications show up, but that's the knowledge that you'll need to bring to bear when you're doing your own feature engineering. So let's look at engineering of numerical features. For instance, when we're imputing missing values, we want to replace them with meaningful values, the missing ones. Then the supervised learning and metric was the training data had no missing values, regression validated by some metric. If we did rescaling or standardization, what were we trying to do there? Modify features with magnitudes that may dominate algorithms. But we can't just do it if it's only a change in units. Otherwise, we can test using regression, similar to imputation. Log or linear transforms, modifying data with more features than needed. These tend to come with their own metrics, for example, a thing called principal component analysis, validated by explained variance and beta confidence scores. So engineering of categorical features, we did one-hot encoding. We were trying to map each category to a vector in an orthogonal basis of a vector space. So supervised learning and metric used. Typically, this removes an obvious bias in what would be a sequential representation, and we can test it using a multi-class confusion matrix and related metrics. Grouping and splitting, rearranging data so that features better reflect their domain relationship to the application. Now this is where you're going to have knowledge of the actual domain. You'll need to be a scientist, not just somebody that knows data. And typically you can test with multi-class confusion matrix. So multi-class confusion matrix is where we have predictions of labels L1 to Ln across the top, actual numbers down the sides, and then we have true labels and false. We can define a concept of precision for label 1. It's the true label 1 over the true label 1 plus the F21, F31 up to Fn1. In other words, the true label 1 divided by the sum over the first column. Notice that if we take sums of rows, we get the number that are labeled, that are actual that label. So the sum of the first row is the number actually labeled L1, second L2, third L3, and so on. So we'll be using normalized confusion matrices at times. That's where we divide the first row by the number of observations that are actually labeled L1. The second row actually labeled L2 as the divisor. Third row actually labeled L3 as the divisor, and so on. Notice that the diagonal entries, therefore, are true positive rates. Also notice that the sums of the rows are all now 1. So what about engineering entire data sets? There you want, for instance, numerical representations of unstructured data. Well, why do you do that? Well, you want vector representations or tables of some kind. And you can test this often by word or document, and typically precision recall curves are used. So let's recall precision and recall. So we've already seen these metrics for validation or testing for a binary classifier. But let's imagine that we have no observations that are true positive, so the recall is 0, and then we progressively classify the true positives until the recall is equal to 1. The result is that precision can be thought of as a function of recall. So for an extremely positive classifier, if all t observations are classified as positive, then true positives is p and false positives n. Recall is 1. Precision is p over the total number of observations. The extremely ideal would mean that there are no false positives. The true positives are all the positives. The recall would be 1. The precision would be 1. Extremely negative, true positives is 0, false positives is 0, and therefore the precision is indeterminate. But if true positive 1 is false positive is 0, then recall is approximately 0 and precision is equal to 1. So 0, 1 is interpreted as the point associated with extremely negative. So if we put this in a unit square with precision as the vertical and recall as the horizontal, then the worst case is the 0, 1 point, and now the 1, 1 point is the ideal. That's kind of our goal. And what we're going to do is we're going to let little r denote the actual recall, little s denote the actual precision. Then p over t is what we get with a recall of 1. And we get a curve. In fact, it's a function. The precision is a function of recall. If we're extremely random, what happens? Well, we have QP positives that are labeled positive and QN negatives that are labeled positive. So the recall is Q. The precision is P over T. And that means we have, at the P over T level, we tend to think of T as being rather large. And we get this random classifier looks like this. So very far away from the ideal. So the ideal would be that we could keep precision very close to 1 or even equal to 1 as the recall increases. So that means as the recall goes from 0 to 1, the precision stays up there very close to 1. Remember, this 1, 1 is the target, the ideal. The closer the precision recall curve gets to the ideal, the better. This is what the ideal would look like. Notice the green going across the top toward the ideal point, but it's going to have to drop down at the end to the T over P point. The area under the curve can be interpreted such that high area under the precision recall curve is close to 1 and a much better precision recall curve than otherwise. Also, we often use the F1 score, the harmonic mean of precision and recall. 0 less or equal to F1 less or equal to 1, closer to 1 is better. What about clustering? There you want to do clustering because you may want to remove outliers or group or split the data maybe into smaller problems. So you can use cluster membership as a response in a supervised learning algorithms, and there are many metrics specifically for clustering. So for example, let's look at intra-cluster and nearest cluster distances. Each data point is in only one cluster. We'll call that one C sub m for x sub I. Little a sub I is this 1 over the number of points in the cluster times the sum of the distances from the xi to the xj points in the cluster, where d here is some kind of a distance measure. This ai is called the average distance from the point to other points inside the cluster. It's also known as the mean intra-cluster distance for a given data point x sub I. B sub I is where we take the minimum over clusters other than the M cluster. So K cannot be equal to M. But once again, it's an average. It's the average distance from the xi to the next closest cluster. So it's the smallest mean distance from xi to another cluster, or the mean nearest cluster distance. So the silhouette index is defined to be the difference between BI and AI over the maximum of AI and BI. This is if we have more than one observation in our cluster. Otherwise, the silhouette index is 0. So by definition, -1 is less than or equal to SI is less than or equal to 1. Notice that the silhouette index is a metric for each observation in the data. And this means it's a per observation, a per point metric. Very useful. We'll see more of these later. But let's try to understand SI. And the best way to do that is with examples. So here's some kind of a set of data in clustering. Suppose we look at this point in the middle of one of the clusters. Then AI is the average distance to other points in the cluster. And it's much smaller in this case than BI, which is the distances from our given point xi to the nearest cluster other than the one we're in. So notice that if AI is much smaller than BI, then BI minus AI is approximately BI, and therefore the silhouette index is approximately BI over BI, which is 1. Let's suppose now we had this point, xi, which is in this blue cluster. In this case, the a sub I is distances to other points in the cluster, and it's about the same as b sub I, which is the distances from that point to points in the nearest other cluster. So that means that BI minus AI is approximately 0, and the silhouette index is approximately 0. So these are only a few of the feature engineering techniques, and this is only a very few metrics. We'll see more, some more useful than we've already seen. See, algorithms differ primarily in how they use the data that's available. Now, neural networks will be an exception. I'll talk about that later. But metrics are at the heart of data science and analytics and predictive modeling. The ability to assess outcomes is at least as important as the ability to produce outcomes. And typically, a well-assessed simple algorithm is sufficient and may be preferable to something more complicated. Metrics are also at the heart of feature engineering.